Hello, my name is Professor Paul Villeneuve, and I will be co-teaching this course with Professor Dvorak. And we will be finishing up the introduction to this course. So here is an interesting slide, and encourage you to take a look at EIA, which is a government agency, and all this information is readily available. And it shows you some anticipated renewable energy generation scenarios from 2011 to 2050. And one of those is based on the generation that we see today. And then the other one is based on limiting the projected rise in temperature to no more than 2 degrees Celsius by the year 2050. And you can see the mixes as it goes up from left to right. And you can see 2022 data. You see high zero carbon technology cost case. And then you can see the different types of penetrations of renewable by every 10 years or so. Then you can take a look at our reference case, which is just a typical sort of, like kind of the best of both worlds, if you will, not necessarily high cost, but not necessarily low cost. And then you can look at the zero technology cost. And what you can see are some similarities between the two. And what we see is we've got a huge reduction in natural gas if we want low zero carbon output, and as well as coal, natural gas. So the fossil fuels have reduced significantly. Nuclear is fairly constant, but wind and solar have increased dramatically. Huge changes in the amount of, the renewable resources that we have, the most cost-effective ones that we see. Now let's take a look at oil production. And a lot of this class is based on what is going to happen in terms of fossil fuels. And we eventually will run out. And a lot of it is sort of predictions at this point. But you can take a look and see in this chart, and you can see over time what's going to happen. So the projection is global oil demand will continue to increase. And somehow we have to make up for the demand. So over time, we're going to expect some sort of natural depletion. And this is the sort of low-hanging fruit that is easy to access. And so that's going to drop fairly significantly because all those easy resources have been found. Now we're going to have to use more sophisticated approaches. And that's where we see IOR, which is improved oil recovery, which uses advanced and moderate methods to extract oil. And then we have EOR, which is enhanced oil recovery, which uses intensive and forcible measures to remove some of the oil. So think of the concept of fracking. Unconventional would be tar sands. So restricting or obtaining oil from the tar sands. And then lastly, we have the deep water complex. So for whatever reason, it's in an environment that is particularly difficult to get as compared to today's standards. So it will add a lot of technology or technological challenges to obtaining that oil. Here are some worldwide production changes by country. And this is kind of a busy slide, but it sort of gives you an impression of, kind of what's happening over the time. And you can see some changes in oil prices. You'll notice with COVID-19, you saw a fairly significant drop between the two. Prior to and just after, and then you've started to see that demand has picked back up. You'll also see prices as they go up and down. That's what the blue line is. So the global oil production is in millions of barrels per day. That uses the solid lines and the colors. And then to the right axis is the actual oil price. And you can take a look and see, the changes in there. But you can see the countries, the leading countries. You can see the United States is a fairly big player. Then you would move on to Saudi Arabia, which is, again, a fairly big player. Iran and Iraq are much smaller players, and there are a number of reasons for that. UAE, Kuwait, and then we have another big jump to Russia. China actually produces a fair amount. And then the next big jump is sort of all the combination of, I believe it's Angola and a little bit of Algeria. So you can get a sense of what makes up the pie, but you can see the United States is approximately the largest producer of worldwide oil. Here are natural gas prices, and you can see the variability of natural gas prices. And natural gas is a little bit different because it's much more difficult to store natural gas. You can do it. You have LNG, liquefied natural gas, where you can actually bring it down to very, very cold temperatures, liquefy the gas. And at that point, you have a much smaller area for the same BTU content. So you see a lot of shipping overseas that goes back and forth, and they use LNG to ship the gas. And then once they get to shore, then they convert it back to a gas at a higher temperature. That can be energy intensive, but is a way to move large volumes of gas over great distances. But again, you can see a lot of volatility in the price of natural gas. I included uranium prices because uranium, again, is a concept that if you believe in renewables being the answer, then that's a good start, but we still need those dispatchable technologies. And we'll learn more about that this semester, what is a dispatchable versus a non-dispatchable technology. But the idea is that we want to include what the approximate price would be per MMBTU for comparison purposes. So if you look at this axis, the y-axis, I'm sorry, you can see what the axis is. It's in dollars per pound of, basically it is a non-refined or non-enriched uranium. It's sort of what you would get out of the ground. And it's about 2.7 times 10 to the minus 7 MMBTU is what the cost of nuclear, unrefined or unenriched nuclear fuel. So some more interesting example of crude oil prices. You can see a lot of variability in the price here, but as of August 15th, 2025, crude oil price is about $64 a barrel. So fairly reasonable prices when you look at things over time. What about unconventional oil? So these are some of the different ones. When we looked at our chart a few slides ago, we looked at different technologies. And so these are some of them that they can go ahead and get this unconventional oil. So you're not necessarily going to be drilling, perhaps, although you will be drilling on the in Venezuela, but this is more of a mining and then sort of a conversion process that is worthwhile. But this one's interesting because it shows a couple different things. It shows when does the oil or when does the unconventional oil become economically viable. So the top axis shows, top and bottom axes show the price of $1 per barrel. And when you actually can start to have these other technologies really be able to go ahead and be effective and compete in the market. So we have oil shale. There's about 3,000 billion barrels of oil available, but it's only viable at $60 a barrel. Converting coal to liquid fuel, that is viable at $70 per barrel. And not exactly sure what the proven reserve is there. The oil sands in Canada become competitively viable at about $60 per barrel, and we have about 174 billion barrels there. And then the Venezuela Orinoco Belt, again, that is effectively now, but it is 266 billion barrels of proven reserve there. What about new power plants? So again, this is just a comparison. And if oil is above around $60, you can do a traditional coal-fired power plant. If you want to try to capture the carbon that is produced by the burning of coal, now the price becomes much more expensive. It nearly doubles to $120 per barrel. So a huge change in the price there. Nuclear is between $80 and $90 per barrel is when they become cost effective. So again, these are technologies that have to compete with fossil fuels, not necessarily from a case of producing CO2, but at least of a case of putting up a new generating facility, and does it actually have the ability to compete with fossil fuels? How about wind? So wind, we can see onshore wind is slightly more than $60 a barrel. And if you listen from a few slides ago, we actually said that it's around $65 a barrel is the current cost of a barrel of oil. So you can adjust and figure out, onshore oil is cost competitive. even if you don't include the fact that there are subsidies available from different agencies. Now, if we go to offshore wind, that's a much more complex, and we are trying really hard to figure out cost competitive ways to get that down. I don't know if it has dropped anything because these are older images, but you're still talking nearly $120 a barrel before these are cost competitive. So these need significant government subsidies to be able to compete with fossil fuels. We can see how wind power has grown over time. So again, starting all the way back in 1998 to 2020, you can see how projects come online. And if you look at the color schemes, those are the different sort of transmission operators. So in Maine, we are mostly part of what's called ISO New England. They're the system operator for our area. New York ISO, obviously New York. California ISO, Pennsylvania, Jersey, Maryland. The West, which is not necessarily an ISO. MISO is the Midwest. ERCOT, I'm not sure what SPP is. ERCOT is the Texas Independent System Operator, and you can see a lot of the growth. And one of the things I think is really interesting about the slide is if you look at ERCOT territory, they've had some pretty big additions to the capacity of wind. And the reason why is because Texas has really, really, really good resources, which mean they're economically competitive with fossil fuels. So those projects are being built, not necessarily with a lot of government subsidies, but also because they actually can make money because the wind resource is so darn good in Texas. And if you look at wind maps, you'll actually find that Texas, I believe, is one of the leaders in the country in producing electricity from the wind. This looks at PV. So again, you can see that for the first, 10 years or so of this century, we can see that there were very small additions, but everything was pretty much the same. Residential, commercial, and utility were about the same. But as we progressed in time, you're starting to see a lot more utility scale projects. And again, part of that might be because of, especially in Maine, in particular in Maine, there've been a lot of government subsidies to support that, but it also starting to become more economically viable. And so what we'll learn about in this particular class is over time, you're going to start to see that PV arrays become more efficient, their costs are coming down, and inverter technology is getting better. Transformers haven't really changed all that much, but because of all those technological changes and improvements, we're actually getting more power per cost. So it doesn't cost as much to produce a kilowatt hour today as it does even a couple of years ago. And there are all kinds of reasons for that, but it's mainly because of the PV array efficiency, much improved efficiency improvements there. So here it shows the growth of renewables. And surprisingly, if you were to look at some of the leaders, you start to see a lot more work in China that is involved. China has gone through a process of creating very large dams. And you can say what you want about the impact dams have on the environment, but for the most part, they do a really good job of getting electricity out without requiring any fuel. So you do have some impacts there. So you can't get something for nothing, but you do get a fair amount of wind. And China has gotten some really good good hydroelectric resources as a result. Coal, not really a renewable, but you can see that as a percentage for kilowatt hours, coal has kind of stayed the same, but renewables has increased. Natural gas should stay about the same, and nuclear obviously can stay the same in petroleum. So the biggest jump in 2040 will be because of renewables. How about these renewable portfolio standards? And so this is something that changes fairly regularly. So you have to be mindful to check with your local state to see what the RPS requirements are. But there are various states and they have mandates for how much of the energy is going to be produced in that state has to be from a renewable source. And so you can see Maine is very aggressive, 100% by 2050, which is really interesting because Maine has had a lot of hydro resources for many, many years, producing a fair amount of energy. So meeting some of the goals, I don't know about 100%, but meeting some of these goals may not necessarily be as difficult as one would anticipate. In the other states where there is nothing, it's white, that's a lot of political stuff, and it's just a general interest from whoever is in politics or even just the general population, what their level of interest is in renewables. And so it's not saying anything negative about these states. It's just that, depending on where you look, those states tend to have lower energy costs. So they may not necessarily be as incentivized to put renewables because their electricity rates tend to be so low. So the thought is as we integrate more renewables, the hope is that the costs will come down if you can factor in inflation. But we don't necessarily know if that's going to be the case. In Maine, that hasn't necessarily transpired as of yet, but maybe over time we'll start to see some improvements and the costs will be more flat and we won't see as large a percentage changes in our electricity rates. Big thing here that this shows you the pricing of typical PV arrays, and you can see a huge price decrease when we go back to 2010. So you're talking $450 dollars per kilowatt per watt, I should say. Now you're talking under $1 for some of these utility applications. Residential hasn't come down so much, and the reason for that primarily is because most folks don't want to spend a premium on higher efficiency cells because if they have a roof line, they can put so many cells on there, which can provide almost all of their electricity needs. So there's no advantage to putting it into a smaller footprint when you have the space already. Whereas when you're talking about a utility application where land is expensive and it's about $4 a megawatt for PV, now you're talking about, okay, if I can save 10, 20% of the land costs, I don't have to lease that land, I don't have to buy that land, pay taxes on it. And so it's worth it to me over time to pay for a premium on the higher efficiency PV arrays. So just a couple terminology things, because this is something that a lot of folks get confused about, but we want to make sure that we understand the difference because we oftentimes will talk about a kilowatt or megawatt, and we'll compare that with a kilowatt hour or megawatt hour, and those terms can be very confusing. And so what we're going to try to do is figure out the difference. And so energy is over time. That's a consumption. So you are consuming energy, meaning you are consuming joules, or you are consuming watt hours, because a watt is a joule per second. And when you multiply that by hours, which has eventually you can convert that to second, then you're ending up with joules only. So they need to be understanding that that is energy. That's the one that we consume. And that's what your electricity bill is based off, kilowatt hours. Whereas power is a rate of usage of energy. So if you have a motor that is rated for 10 horse, that motor can put out the equivalent of 10 horsepower on the shaft, and it can do that for 20 years. It is going to use considerably more energy than what the 10 horsepower equivalent would be because you need to add the time part in there. So as electrical engineers, we often talk about things as watts because that helps us size the infrastructure. We'll use the term infrastructure. And we'll get more into it and it'll make more sense of different terms. But over time, we will rate the equipment. So all the feeders and transformers and all that stuff is based on a continuous rating. What can that handle? What can that equipment handle before it starts to get damaged because of heat built up or whatever? So that's a joule per second is typically what we're talking about here, but we just talk about it in terms of watts. Interestingly enough, our installed capacity in the US is about 900 gigawatts, and the peak load in New England is around 28 gigawatts. So that's an approximate. That changes obviously slightly depending on a couple of things, but it's usually going to happen in the summer, and it's very heavily weather dependent. So extreme heat and humidity days tend to be pushing that 28 gigawatts value. So interestingly enough, for the economics of renewable energy, we install a power plant capacity. So that means we have a generator that can produce or generating facility that can produce 10 megawatts. And we have capital costs and O&M costs to install that capacity. But we are not selling capacity. We are really selling joules or kilowatt hours or megawatt hours. So we are getting paid for the joules that we provide to the grid if you're operating a power plant. You still have to build a power plant and you have to provide the capacity so you can support whatever your performer for your business case looks at. You want to be able to provide so many kilowatt hours. And so your plant might be bigger if you don't have a high capacity factor. And again, we'll learn more about capacity factor as we go along. But if it's a very high capacity factor, the rating of your plant perhaps could be reduced if you're trying to provide a certain number of kilowatt hours. So we have to balance capital and operating costs because we can build the most amazing power plant that's efficient and doesn't produce any emissions, but we would most likely have extremely high operating costs. And what I mean by operating costs is you have to pay back the loans for getting the capital to build a plant. So not only is it the fuel costs and O&M costs, but it also is paying back the loans. And again, we'll talk about those terms as we get more and more into the semester. So nuclear and solar have very high capital costs, but their operating costs tend to be very low. Nuclear plants have to be extremely well designed, or else we're going to have some serious issues. Solar takes a lot of land to build them, and the arrays and the inverters take a fair amount of cost. But again, you don't pay anything for the fuel. And with nuclear, the fuel costs are relatively cheap. Natural gas and oil tend to have pretty low capital costs because these plants are very well known. They've been designed for many, many years. People are extremely familiar with gas and oil plants and the technologies. We know boilers, we know turbines, we know those inside out because they've been sort of perfected over the last 100 years. So those have very low capital costs because there isn't a lot more design that needs to be done. They've been built for many years, so construction costs tend to be low. But what is very expensive about our facilities is they have very high operating costs. And those are almost always attributed to the fact that we have to buy fuel. So for every joule or kilowatt hour that we're producing, we have to have a fuel source that we're paying for to do that. And then coal, wind, and hydro are in between the capital and operating costs. So again, we're talking about a mix of different technologies to be able to meet that energy puzzle, if you will. So we'll start to learn the difference between baseload plants and peaking plants. And if you think about baseload plants are plants that run for very, very high percentages of the time, whereas peaking plants hardly run at all because they tend to have very, very high fuel costs. And so you can perhaps see that you need a bunch of different technologies here to meet all those criteria. Earlier, we talked about capacity factor. So the capacity factor has a title that it says, if you have a 1 megawatt power plant, the capacity factor is a ratio of if that 1 megawatt power plant ran for the year, how many joules could it produce? And the higher the capacity factor for a particular facility or technology, the lower the cost per kilowatt hour has to be in terms of its installation. So if I can build a 1 megawatt power plant and that serves all my need, I should have lower capital costs than if I had to build a 10 megawatt power plant because my capacity factor was much, much lower. This carbon tax, and again, we're giving you a lot of different technologies and we're trying to be consistent in terms of what is happening. I know that there's a lot of political changes and we don't know necessarily what the future will hold, but we're trying to give you a broad perspective of the different things. And so there is this regional greenhouse gas initiative. It's with 9 states, and you can see the states here. But essentially, they have set up a market to trade carbon credits. And so these states will come up with a certain number of credits based on the generation. And then you're allowed to produce a certain amount of carbon. And if you exceed that, you have to go out into the market and bid on these carbon credits so that you can actually produce more carbon. So it's a way of encouraging companies to try to figure out how to reduce their carbon footprint. It's been around for many, many years. I don't know how effective it is. It's really behind the scenes, but you can read more about RGGI if you want to find out some of the market things and the business things and the government regulations that have really been put in place to sort of help control things. Here are some typical capacity factors, and the higher the number, generally the better it is. And what I mean by that is your number, if it's very, very high, then that tends to mean that, yeah, that plant is running as almost at full out for the entire year. So you can see biomass has a capacity factor of 1 at its peak, but it's all the way down at 0.35 or so at its minimum. So that has a very wide variance. So that can cause you some real issues there. Some of the other ones, coal, very well built, very well designed plants. So when they're operating, they are base load plants. They run for long periods of time and don't change their power levels. Same as this combustion turbine, combined cycle turbine. They tend to have pretty high efficiencies. They're expensive, more expensive to build than just a standard combustion turbine, but they run at higher capacity factors. They tend to be more efficient and they use their fuel more effectively, so they run more often. The highest of the bunch is nuclear. You can see that those are 90%. And again, that's all because of a nuclear power plant. It's got to be well built because you can't handle an accident and release radiation. That would cause serious issues. And so super well designed, super well tested and maintained. And as a result, they hardly ever trip. So there's almost no variability in nuclear. And then the other technologies tend to be a lot of renewables, and you can see a lot of variability there, but you can also see pretty low capacity factors. And what we'll learn is with solar and wind, it's all based on what the wind resource or the PV resource, the sun resources. Obviously, solar, if you build a 1 megawatt facility, well, at least a third of the time, it's not going to be producing anything because it's the evening. There's no sun. So as a result, you get less than a third, I mean, less than 2/3 just from walking out and building a facility. Forget about the fact that you have an array that has a certain efficiencies. It's just at nighttime, there's nothing there. Same thing with wind. When the wind turbines don't always blow at a constant speed day and night, although they're higher than solar, and you can see with wind, they tend to be higher than the solar because again, you don't have to worry about the night thing, but they don't always have that constant wind, so you can see some variability. It's less variable when you're at an offshore wind resource, and the reason for that is because the surface of wherever the wind is going over has a pretty big influence on the consistency of the wind. So if you think about the ground, we have mountains, we have buildings, trees, all that stuff. Those tend to impact the wind speed and slow things down. When you're out on the ocean, there's way less variability because you don't have buildings and trees and all those different things that are slowing the wind down. It's basically a very slippery surface from the concept or from the perspective of the wind. So yeah, so anything with a fuel source, even geothermal, landfill gas, biomass, they tend to have an higher average capacity than the non-dispatch technologies. But you can see that there's a lot of work to make these improve, but there's only so many things we can do to do that because a lot of it is based on not necessarily the technology, but on the resource itself. Here looks at some costs and average, including capacity factor. And you can see this is older figure, but it's hard to get updated ones. But this shows you $2,006 per kilowatt. You can see solar is pushing about 6,000, all the way down to a simple cycle combustion turbine, which is less than $1,000. So you can see why fossil fuels remain so competitive because they have very, very low cost, relatively speaking. Here are levelized costs, and as we go through the semester, we will learn more about levelized costs for power plants, and you can look at the different technologies. We have dispatchable or non-dispatchable. Dispatchable, all that means is we have some sort of a fuel available to us, so we know that when we ask it to turn it on, it's most likely that the facility will turn on and be able to produce power. So we can see that we have combined cycle, which is having a capacity factor very high, 87%. Its capital cost is about $9.36 per megawatt hour. Has fixed O&M 1.6. It's variable, including fuel, 27.7. Its transmission investment, 1.14. So its total levelized cost is around $40 per megawatt hour. Now we move over to, let's take a look at nuclear. So nuclear has a very high capacity factor, but its capital cost is very, very high, extremely high. Its fixed O&M costs, again, these are well-maintained facilities, so their O&M costs tend to be very, very high. But when I look at the fuel, for the variable, we see a pretty big reduction there. Transmission investment tends to be low because we don't have to we have a transmission facility that has to be built, but it's almost fully utilized. So the cost per megawatt hour tend to be less. So that's about twice what it is from there. So let's look at some different technologies and see where we can be competitive with a combined cycle power plant. And we can see once we go to the non-dispatchable technologies, now you can see wind has a close approximation to combined cycle. Solar PV has a little bit less. So you can take a look and you can see how there's some real variability, if you will, in the cost. So this just gives you kind of a ballpark amount of what the levelized cost will be to build these plants. So this is my last slide, but here's our course progression. Because the name of the class includes the concept of electric, we're going to be talking a little bit about electric circuits and power, because Professor Dvorak and I firmly believe that renewable energies will not be effective or will not have higher levels of penetration until such time they can integrate to the grid. Because we're very comfortable using the grid, right? You're all connected, plugged in with computers or your cell phones or whatever, the lights are on, and that's all based on being interconnected to the grid. So once we utilize the grid more efficiently and maybe make the grid even more powerful, meaning adding more stations and making it with bigger conductors, et cetera, we'll be able to integrate more renewables and be able to do more work with it. So the concept of using EVs, electric vehicles, to do transportation is going to be more effectively utilize the grid. And then the concept or the hope is that you will use less fossil fuels, less CO production to, basically you do your transportation. We'll talk a little bit about the electric power industry, because if we really want to grow renewables, as we just mentioned, we really need to grow the utility industry. So we have to talk about how regulated it is and how we can effectively use the current configuration so that we can get more and more out of our utility system. We'll talk about distributed generation. That term is changing a little bit. It's called distributed energy resources, or DER, because battery technology can either be a load or a generator. So there is some discussion about, switching over. We have CSP, biomass, fuel cells, and we'll also talk about some of the economics of distributed generation. So keep in mind, these are all smaller scale plants because they're distributed out near the load. They are not necessarily massive power plants producing power for multiple cities or sometimes even an entire state. We'll discuss hydropower, because that's been a renewable energy source that's been economically viable for many years. We'll talk about biomass and some of the alternative fuels. We'll do some wind power analysis. We'll look at the different types of turbines and how we convert mechanical energy, right? The power in the wind, we'll convert that to electricity. We'll look at wind farms. We'll do the same thing for solar and, kind of go through the same process we did with wind, or how do we convert the sun's rays into electricity? And then how do we integrate that and connect that to the grid and then sell the power? We'll talk about geothermal power. We'll look at some energy storage, not just exclusively batteries, but pump storage facilities work really well. And then we'll talk about wave and tidal power. So that is all I had for our first introduction. I hope you have a wonderful day, and we look forward to seeing you soon. Take care.